Hi all, welcome to a new video lecture on design and analysis of algorithm. So here we will discuss in the previous video we saw what is basically an algorithm and what are all its characteristics, right? So you got a minimum understanding. Now it's time for us to explore more about algorithms and let's see the terminology, that is correctness and optimality. Okay, so let me start with an example. Right, you know how to find out maximum in an array, so we can start with that, right? So the problem is, so let me write it as the problem is to find maximum in an array. Okay, so let me call the array as a, and you know a number of ways to do it, right? So let me write it like this. Algorithm 1, or the first procedure that you can think of is, so you can declare a variable, say max, and you can assume that the first element of the array, so assume that the array index is starting like 1 to n, like that. So you can assume anyways. So the first element of the array you are assuming to be the maximum, and then what you can do is you can run a for loop that is varying from I equal to 2 to n, or length of the array, and at every iteration you can check whether the ith element of the array is actually greater than the assumed maximum. So initially we don't know, we assumed that the first element of the array is the maximum. Then by a continuous linear procedure, one after another, we are exploring each element of the array and we are checking whether it is greater than this max. If that is the case, you will reset this maximum with this a of I, right? So at every iteration we are having the guarantee that this max variable is containing the largest element. And finally, once you come out from this for loop and if loop, what you can do is you can simply return the maximum element back to the main function or something. So from where you are calling this, so I'm not writing it like a program, so just the algorithm notion only I'm highlighting. Okay, so you know how to implement it using any given language. Okay, so you got it, right? So this is one way of doing it. Okay, now can you tell me some other way of doing the same? So one easy thing that you can think of is you can simply sort the array A, right? So you can say in increasing order, ascending order, so that the last element of the array will be your largest, right? Return A of n. Or if you are sorting the element in the decreasing order, the first element of the array will be the largest, whatever it is. So that's all, only 2 steps. But you have to think about the time taken for this sorting procedure. Anyway, that we are going to see in detail. So for the time being, so this is another way of doing it. Now let me introduce you a third way of doing the same. I mean finding maximum, that procedure. What I am doing is the elements of the array, given array I am denoting like a1, a2, etc. Some middle element an by 2, and the second half is like an by 2 plus 1, etc. to an. Right, now what I am doing is I am focusing on this first half, and from the first half I can find out the maximum using the algorithm 1 or algorithm 2 or some other way. So let me call it as max 1. And now from the second half also I am finding the maximum, say max 2. Now what will be your final maximum? Final maximum will be maximum of this max 1 and max 2, right? That you can simply by doing one more checking you can do this. So that about it, right? So from these this is something what I told you already. Anyway, we will see all those things further. So I did something like a divide and conquer approach, right? Divide and conquer approach. We formally call this kind of algorithms as divide and conquer, and this will come later. So the problem I divide into 2 subparts, and I tried to solve these subparts independently, and finally I tried to merge the solution. We don't know whether it is a better approach or not. Sometimes it can save time, sometimes not. Okay, so this is also a third way of doing the same. So that's all. Now what we understood is not only this, you can take any problem, searching, sorting, whatever it is, any computation problem you can think of, and you can see that there are many approaches, right? Many approaches, or this approach is what we formally call as algorithm, right? Algorithms for the same problem, right, for the same computation problem. So it's better to highlight this term, computational problem. Now out of all these different approaches, one can think about which is the best one, right? So that about it. So out of so which will be best way to solve the problem. Okay, so that about it. Now let me ask you one more question. So that is something you are supposed to ask at the very first point, whether the problem itself is solvable. So if you have a solvable problem, then it is a time for you to think about different ways of solving it, right? Sometimes the problem may not have a solution, so that also possible. So what we can do is, so some kind of classification of problems we can think about at this point. So basically, if you are looking at the field of computer science, it is essentially focusing on something like whether a given computational problem is solvable or not. So that is one way of thinking. So basically that is what we are doing in computer science, right? Fully right, in whichever field you are looking at some way of handling certain problems. So that is the main thing, right? So the focus of the branch computer science is basically something like given a set of computational problems. So that can be from any domain. Okay, so it can be from physics, chemistry, or something else, or something which we are interested, maybe a graph problem, number theoretic problem, whatever it is. Okay, computational problem, or you can think of a single problem or a set of problems. So the question is this problem solvable or not? Okay, sometimes you can see that the problem is solvable and sometimes it will be unsolvable. So what do you mean by a solvable problem? Okay, solvable means there exists an algorithm, right? There exists an algorithm. Algorithm is basically some kind of mapping from the input to output, right? So I can also call as a mapping from well-defined set of inputs to outputs to convert any input instance to appropriate output. So that is what we can call as an algorithm. Now the thing is that if no such algorithm exists, right? So unsolvable means no algorithm exists. Now if you want, you can highlight something called what I can tell you, no finite algorithm. Okay, so I don't have to highlight this term actually, because algorithm by default, what we mean is algorithm should be finite, right? So if I am saying that algorithm exists for a problem, what I mean by default is finite algorithm. Okay, so there is no doubt in it. So why I am highlighted that term is sometimes you may think of a brute force approach or something which will take years and years, it keep on running, but it is not giving you the solution. But at some point, at some later point, it may give you the solution, but you are not interested on it, right? So if you are getting a solution, you should be able to get it in a finite amount of time. That finite doesn't mean that I need the solution within 1 second or 1 minute or 1 hour. Let it take 6 months, fine, but I need a solution within finite amount of time. If such an algorithm exists, I can call the problem as a solvable problem. If no such algorithm, it will be a unsolvable problem. Now this is something that we will handle separately. Maybe we will see some more glimpse about this unsolved problem maybe in your last module, but throughout the subject, 90% of the course, we will be seeing a different solvable problem, and we will be looking at their efficiency, like which will be better and how we can improve its efficiency. So that kind of things we will be looking mainly. Okay, now the thing is that once the problem is solvable, then you can ask many questions like how many solutions exist, right? So how many different algorithms exist? And once we have a number of algorithms, how do we compare them? So then only you can find out the best one, right? Compare them or compare these algorithms. So after comparing, ultimately what you are trying to do is to pick the best one, right? So how to do that? How to pick the best one? So this is where we bring the notion of efficiency, right? So this is where one can think about something called as efficiency. So I can say that this algorithm is efficient, so I am picking it as a solution for my problem. I'm not going to use something other than some other way of doing the same one. Okay, because this is efficient according to me. The efficiency, this terminology will seem more like a time complexity analysis, space complexity analysis, like that we will explore this. But anyway, so we are just in the beginning, right? So we are just looking at the problem and different ways of doing it. Okay, so that about it. So once the problem is unsolvable, so that is something different, so we will be handling it in a different way, so that we may see later. Okay, now let me introduce something called as the correctness and also this optimality of the problem. So it is something like that. So let me write it like this: as part of algorithm design, we are interested in the following, right? So the first parameter we are interested is correctness. So now it is the time for you to design an algorithm. So after the proper design of an algorithm, you can think of its analysis. That is the second part. So where this optimality terminology will come. So right now we are at the design phase. So once you are designing an algorithm, you, as the name says, it should be logically correct, right? So whether the algorithm is doing what it is intended for or it is doing something else, you are simply writing some code and you are saying that this is a solution to the problem, is it so? So that you have to guarantee, right? So as a developer or as a person who is having the idea, you should convince others that this is a correct idea. Okay, so that correctness should be ensured. So how we can, or simply what is correctness? So let me write like is the strategy which I am proposing, okay, is the strategy or the approach, or I can call it as the algorithm, right? Whatever it is, designed by me performing the intended task. So the intended task, or it is doing something different, right? For example, simply if you can look at that searching algorithm, and I know that an element k is belonging to the array, right? Array, then the algorithm should say yes. But assume a situation that the element is already there in the array, that we all know, but the algorithm is answering you no. So that is a wrong algorithm, right? So the correctness is not ensured. Similarly, if the element does not belong to the array, then the algorithm should output like a no. That is the default behavior. So that is what we call as a correctness. If it is answering something different, it is not ensuring that correctness, right? Now how you can ensure this correctness? There are formal ways of doing it. Simply by looking at the algorithm, somehow we may be convinced like it is correct, but mathematically, you can use certain tools that you studied in your discrete mathematics course and all, like some proof technique, many things, right? So those things, or their advanced form, we will be using to show that a given algorithm is correct. So that is actually the design part. So once you are proposing a new algorithm, you are supposed to ensure that it is your responsibility to convince others that your algorithm is correct. So for that you can depend on the mathematical tools that you studied in your discrete mathematics courses and all. Okay, so accordingly we have a formal mathematical way of showing that the given algorithm is logically correct. Okay, so that is one part, but anyway in our course we are not looking at the correctness part, how to show a given algorithm is correct. So that is something when you are proposing a new algorithm you are supposed to think about it. So what is happening in our courses, we are studying many algorithms proposed by other people, right? So that time you don't have to think about the correctness. Someone else already already showed that its correctness and all. Anyway, in that view, so you can assume that what are all the algorithms given in your CLRS textbook, right? So it is correct. Okay, so its correctness is already proved. Okay, so that about it. So I am just introducing that concept only. This we are not going to see in detail anyway. So that is something mandatory or minimum for a logically means whenever you are proposing an algorithm, it should be logically correct. Okay, so that is minimum requirement. Now the second thing is regarding optimality. Okay, so what I am trying to say is, suppose I have a computational problem, right? Say a problem P. Now different people may come up with the different approaches for this, like this is A1, this is another algorithm A2, this is another algorithm A3. Now for the time being I don't know how to find out the best one. So what I am doing is I am simply executing the algorithm on a particular platform, on a given platform, maybe some Intel i5 something. Okay, so for a given set of specification I am running the algorithm and I saw that, but the actual way of doing it we will see later. So right now, so something that is coming to our mind by default is what I am telling you. So and we observed that this algorithm 1 is taking say some 10 millisecond of time, and this one is taking say some 100 microsecond of time, and here at this point I improved the algorithm in such a way that maybe 1 nanosecond of time, right? You know this milli, micro, nano, this is something like a 10 power milli, I mean 10 power minus 3, right? Micro 10 raised to minus 6, this is like a 10 raised to minus 3, right? So like that I have 3 approaches. Now can you tell me which is the best one? So definitely you will answer it like a A3, right? A3 is best. Why it is so? Because it is taking the least time, of course. Now the question is, can we better A3? In the sense, can I come up with an algorithm which is taking less time than what is taken by this A3? Like A3 is taking just 1 nanosecond of time only. So can I come up with an algorithm which is taking less time that? For example, after some years and all, a person come up with a fourth way of solving the same problem. I am not talking about the problem, it can be anything. I am just telling it in a general way. It's a computational problem, okay. And the algorithm is taking just 0.1 nanosecond of time. See, now definitely you know A3 or sorry A4 is the best out of all the existing one. So we are just looking at the time analysis only, but in reality space, complexity and many other parameters we will analyze. So as of now this is the only measure we are having to find out the best one. So that's why we are going with that. Okay. Now again you will ask the same question, right? What is that? Is the algorithm A4 best ever possible, or is anything better possible? Okay, so you can think about it, and suppose you got the answer as no, then you can conclude that, so that means it's not possible to come up with an algorithm which is better than A4. Suppose you know it or you proved it somehow, this is a point you can see that like algorithm 4 is optimal. So this is about optimality principle, okay. It's not optimality principle, the notion of optimality, okay. I can say that A4 is the optimal algorithm. And basically the study of Optimality. Optimality is to find such best ever algorithms, right? Like what we saw already. So this is by this let's conclude this video lecture. So what I was trying to say, I have different algorithms for solving a particular problem. Now the first question is whether the computational problem, say P, is solvable. Okay, whether the computational problem, whether P is solvable, whether there exists an algorithm for it. If yes, then you will be asking what are all different ways to solve, right? Different ways to solve it. Now someone is answering you like A1 is one approach, A3, A2 is another approach, A3 is another approach, A4 is another approach. For the time being only 4 approaches, or you can think about more. Okay, so and accordingly I find out the times like say 10 millisecond, I'm not remembering what are all the time, 10, 100 microsecond, 100 microsecond, 1 nanosecond. So I keep on improving that. So every time I'm trying to improve. So 10 millisecond was my initial approach. Then I improved to 100 microsecond. Then it was 1 nanosecond. Then I am having something which is taking only 0.1 nanosecond. So at this point I concluded that this is optimal. This is how I concluded that, because I have a mathematical way. Again, these things are not something like simply somebody is guessing, so somebody is feeling. So it is not like that. Everything should be proved in a systematic way using the mathematical tools. Okay, so that is how this mathematics is especially the discrete mathematics tools is closely related with computer science. So this is something that involves purely mathematical concept. So when you are going it in detail, so anyway in your course, as it is a UG level course, we may not look that much mathematical concept. In a way, very basic way only we will proceed the course, but later on when you are doing your PG or some higher courses, PhD research and all, and that time you will explore more mathematical ways of doing so many things. So once you are coming up with the algorithm, so definitely you have to think about the correctness, right? Correctness, right? And after that, so here we formally proved that A1, A2, A3 they are all logically correct. That is then only you have to think about it further, otherwise it's meaningless. So that point you have to think about their running time, and this running time for the time being we don't have any other measure. That is why we are taking it everything in second, but as I already told, it's something platform dependent analysis. We don't want it, right? So we need something that is independent of the underlying architecture we are having. So anyway, so as for at this point we don't know much about it. We are assuming for a given article this is a performance. So now every time when you come up with A3, you ask that question whether can I better A3, right? So can I come up with a better one? Yes, A4. So can I come up with a better one? No. So that is the point where you answer it like a optimal algorithm. So right, so we have to use sophisticated mathematical tools to prove the optimality. So the it should be, it's not something randomly we are saying, we should prove it, right? But anyways, so this is the overview of the concept. So here we discussed only two important terminology. What about correctness of the algorithm and what about the optimal solution? Okay, so that about it. Maybe more details we will see in subsequent video lectures. Thank you.